Chapter 2, Measurement. Now, this is part 1 of the topics on measurement. In this chapter, we shall discuss various units of measurement, and we will also introduce the SI system of measurement. But first, let's go back and see how things evolved over time. Now, before the scales were invented, people used to use the width of their hand or length of their arms to measure the length of something. So for example, the length of this table can be said to be 5 hands. Essentially what we are doing is comparing two lengths. We are saying how many times is one length in terms of another. So a measurement of any kind is basically a comparison with a known standard, and here we are using the length of the hand as the standard. The problem is that everyone's hand has a different width. So as long as we need a crude estimate of length, it was okay. But when more accurate measurements were required, for example in construction of buildings, that kind of crudeness could not be acceptable. So what do you think they did to get a standard measurement? Usually, it would be the king's hand that would be used as a standard. Somewhere between the 12th and 13th century, King Henry of England decided that in his kingdom, the unit of measure of length will be called a yard and will be the distance from the tip of his nose to the end of his outstretched arm. And of course, a primary scale was made from this measurement. And from this primary scale, secondary scales were manufactured and distributed to everyone. So let's begin by defining what a measurement is and what it actually means to measure something. In science, a measurement is considered the assignment of a numerical value to an object's physical property. Measuring physical properties is very common. For example, you might want to know the length of a line, the volume of a sphere, or the density of a liquid. Whenever we take measurements, we also have to assign units to the numerical quantity in order to convey the relative size or magnitude of the property in question. For example, if I said the length of my shoe was 10, you wouldn't actually know how long the shoe was because there will be no context for what the 10 represent. In fact, this will only make sense if the number 10 had a unit of measure to go along with it. Any physical quantity such as length, mass or time is measured and denoted in terms of basic standards called a unit of measurement. A unit is an internationally accepted basic reference standard against which the measurements of various physical quantities are compared. In physics, we deal with many physical quantities and their units. However, very few basic units are required to express these physical quantities. Previously, different units of measurement were used in different parts of the world. For instance, some places used centimeters, others foot, and others meter, all to express length. Grams, pounds, and kilograms were used variously to express mass. And of course, this brought a lot of confusion amongst the scientific communities when it came to sharing of information. So there was need to have a universally accepted system of units that will be used all over the world. In 1971, a General Conference on Weights and Measures recommended a set of standard units of measurement with their symbols and abbreviations. This system is known as Système International d'Units, French for International System of Units, abbreviated as SI. The SI system is currently used globally for all scientific, academic, technical, and industrial purposes. The SI system has 7 basic physical quantities, their units of measurement, and the symbols. Length is measured in meters, denoted by the small letter m. A meter is the length of the path traveled by light in a vacuum during a time interval of approximately 300 millionth of a second. Mass is measured in kilograms, denoted by the small letters kg. A kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at the International Bureau of Weights and Measure near Paris in France. Time is measured in seconds, denoted by the small letter s. A second is the duration of approximately 9 billion periods of the radiations corresponding to the transition between two levels of the cesium-133 atom. Electric current is measured in amperes, denoted by the capital letter A. An ampere is that current which, if maintained in two straight parallel conductors of infinite length and negligible circular cross-section and placed 1 meter apart in a vacuum, would produce a force equal to 2 times 10 to power negative 7 newtons per meter between the two conductors. Thermodynamic temperature is measured in Kelvin, denoted by the capital letter K. A Kelvin is equal to 1 over 273.16 of the thermodynamic temperature of the triple point of water. Luminous intensity is measured in candela, denoted by the small letters CD. A candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 5.4 times 10 to power 14 Hertz. And finally, amount of substance is measured in moles, denoted by the small letters MOL. A mole is the amount of substance which contains 6.02 times 10 to power 23 particles or entities. Apart from these 7 basic units, the SI has defined another unit for a supplementary quantity, the plane angle. Plane angle d theta is the ratio of the length of an arc of a circle to the radius of the circle and is measured in radian, denoted by small letters RAD. A radian is the angle subtended at the center of a circle by an arc equal in length to the radius of the circle. Most physical quantities are expressed in terms of the basic quantities, also called the fundamental units. The other quantities which are expressed in terms of basic quantities are called derived quantities. For example, area. If we take a line that is 2 meters in length and then create a square from 4 of these lines, we can find out the area or the two-dimensional space that this square occupies by squaring the length of the original line. So we have a unit called meter squared. It is a derived unit. The basic and the derived units together make up a system of units, a generally acceptable set of units of measurement. We shall look at the most commonly used quantities: length, mass, and time. So we start with length. Length is a measure of the distance between any 2 points. Other terms used to describe length include height or depth, circumference or perimeter, radius, diameter, and so on. The SI unit of length is meter, but smaller and larger distances can be given in multiples of a meter. length can be measured by estimation or accurately by using measuring instruments. There are various instruments used to measure length, and the choice of an instrument depends on the size of the length to be measured and the level of accuracy desired. At this level, let's just talk about the meter rule. Meter rules or half-meter rules are commonly used in physics. They are graduated in centimeters or millimeters. The item whose length is to be measured is aligned with its one end to the zero mark of the ruler. This paper clip is 3 centimeters long. This is 7 centimeters long. The eraser is 5 centimeters long. The glue stick is 7 centimeters long. And the pencil is 10 centimeters long. A tape measure can also be used to accurately measure lengths. Estimating lengths. Now, in some cases, it just might be difficult to measure some object's length. Consider this streetlight pole. If we wanted to measure its height, we would have to climb to its top, and that is hard. But we could use its shadow to estimate its height because we can measure the length of the shadow. We just need another object whose height we know and have it cast its shadow as well. For example, this man. We can measure his height and the length of his shadow. Let's say his height is 1.45 meters. We measure the length of his shadow, and let's say it's 1.2 meters. The length of the pole's shadow is 8.40 meters. Now, the thing is, the objects and their shadows form right-angled triangles which are proportional to each other. We can find the height of the pole using the relationship height of the pole over the height of the man is equal to the length of the pole's shadow over the length of the man's shadow. So height of the pole over 1.45 meters is equal to 8.40 meters over 1.2 meters. We cross multiply. Height of the pole times 1.2 meters is equal to 1.45 meters times 8.40 meters. We divide both sides by 1.2 meters and we get the height of the pole is equal to 10.15 meters. Now, if you need to find the length, width or height of an object and you don't have a measuring instrument, you will need to estimate. You can do this by comparing its measurement to another object. For example, the height of this kitchen worktop is about 1 meter. The length of a pen is about 15 centimeters. The height of a door is about 2 meters. Use the everyday objects whose length you know to estimate the length of a mobile phone. Is it likely to be 10 centimeters, 3 meters, or 100 centimeters? This is how long it is, so we would use centimeters to estimate its length. We can therefore compare the length of a phone to the length of a pen. If the length of a pen is about 15 centimeters, the phone is slightly smaller in length, so it's likely to be 10 centimeters. 3 meters is 1 meter longer than a door. So the length of a phone is unlikely to be 3 meters. 100 centimeters is 1 meter. This is the approximate height of the kitchen worktop. So again, the length of a phone will not be 100 centimeters. Next, measuring curved lengths. Now, to measure curved lengths, we use a thread. We take a thread and make a knot on one end. Place the knot at the end of the line at P. Hold the knot with one hand and put a small part of the thread along a small part of the line. Secure the thread at point Q, releasing the knot at point P. Do the same along the remaining part of the line and secure it at point R. Continue with these steps until you reach the end of the line. Mark the thread where it lands with the end of the line. Stretch the thread and measure its length using a ruler. The length of the portion of the thread is an estimate of the length of the curved line. Next, area. Now, area of an object is the two-dimensional surface that the object covers. While the side lengths can be measured in any unit of distance like meters, area is expressed in square units, for example, square meters, which is meter squared. To see why, let's look at something simple like a square. Say this square has a side length of 5 meters. How much surface does it cover? To answer that, we can take this line segment that represents one side of the square and realize that to span the shape, we are extending this line segment across the shape. So it's 5 meters length that is being pushed across the 5 meters of the adjacent side. 5 meters times 5 meters gives us 25 square meters. Remember that units will be manipulated just like in algebra. So meters times meters is equal to meters squared, just like x times x is equal to x squared. And so with that, we understand the area of a square, its length squared. We have formulas for calculating areas of plane figures. If it's a rectangle, the longer side is called length L and the shorter side is width W. Area is equal to length times width. So for this one, 6 meters times 4 meters is equal to 24 meters squared. For a parallelogram, area is given by base times height. Remember, the height of a parallelogram is the perpendicular height. Back to the rectangle, if we split it into 2 equal halves, we shall have 2 triangles. Each triangle has half the area of the original rectangle. That's how we get area of a triangle. Area of the rectangle, base times height, and then we cut it into half, so half base times height. So for this triangle, we have an area of 12 square meters. Remember, the base and the height must be perpendicular to each other. This works even if the triangles are not right angled. Even though it's hard to see how this triangle is half the size of the rectangle, we can still use a half times base times height. Trapezoids are a little different. For this, we do a half times height times the sum of the 2 bases. So for this trapezoid, we shall have a half times 4 times 6 plus 10, giving us 32 square meters. When we have shapes that are quite irregular, we break them into simpler regular shapes that are more familiar. For this shape, and given all these side lengths, we can split it into 2 rectangles. Then we just get the area of the 2 rectangles and add them together. Same with this figure. We can split it up into a rectangle and a triangle. We get all the side lengths and plug in the values in the respective formula for area. With circles, area is given as pi times radius squared. For a circle with radius 3 meters, the area will be 28.26 meters squared. Knowing this, we can calculate more areas of irregular figures, like this with a rectangle and a semicircle. We split it up and the rectangular part will be easy. While for the semicircle, we get the radius, which is basically half the diameter. Then we calculate pi times radius squared and cut it into half since it's half a circle. Next, area of irregular surfaces. Now, an estimate of an irregular surface can be made by dividing it into squares, each of 1 centimeter squared. Then we count the number of complete squares. In this case, there are 9. We proceed and count the number of incomplete squares, and in this case, there are 14. Next, we assume that all the incomplete squares are half of the complete ones. It's an assumption. So we divide their number by 2. So 14 over 2 will give us 7 complete squares. So the total number of complete squares is 9 plus 7, giving us 16. And this makes the total estimated area to be 16 square centimeters. Now, you might want to estimate the area of the irregular shape on your screen. So that now we move to volume. Consider a one-dimensional object like this line. We measure it with a one-dimensional quantity called length. This line has a length of 1 centimeter. In area, we saw that if we move or extend this one-dimensional line in a direction perpendicular to it by a distance of 1 centimeter, it forms a two-dimensional object called a square. Two-dimensional objects are measured by two-dimensional quantities that we call area. Because the original line was 1 centimeter long and we extended it by a distance of 1 centimeter, the amount of area that this square occupies is 1 square centimeter. Now, imagine that we take the two-dimensional square and move or extend it in a direction perpendicular to its surface by a distance of 1 centimeter. It forms a three-dimensional object that's called a cube. And to measure a three-dimensional object like this one, we use a three-dimensional quantity called volume. Volume is how much three-dimensional space an object occupies. How much volume does this cube have? Since it was made by extending 1 square centimeter surface a distance of 1 centimeter in the third dimension, we say that its volume is exactly 1 cubic centimeter. Since cubic units are made by multiplying 3 one-dimensional units together, like centimeter times centimeter times centimeter, we abbreviate them using the exponential notation centimeter to the third power, or centimeter cubed. A lot of three-dimensional shapes can be formed by taking a two-dimensional shape and then extending it along the third dimension. For instance, if you start with a rectangle and you extend it along the third dimension, you get a three-dimensional shape called a cuboid. If you start with a triangle and then extend it along the third dimension, you get a three-dimensional shape called a triangular prism. If you start with a circle and extend it along the third dimension, you get a three-dimensional solid called a cylinder. There are usually general formulae for calculating the volumes of these three-dimensional shapes. All you need to do is get the area of the original two-dimensional shape and then multiply that by the length or the distance that was extended. Usually, the original two-dimensional shape is called the base of the object or the cross-section. Starting with this cuboid, the base is the original rectangle, and its dimensions are 4 centimeters by 3 centimeters. So to get the area of that base, we multiply the lengths of the dimensions together. 4 centimeters times 3 centimeters gives us 12 square centimeters as the area. Now to find the volume, we multiply that area times the length the base was extended. This was 10 centimeters. So 12 square centimeters times 10 centimeters, we get 120 cubic centimeters. That is the volume of the cuboid. How about the triangular prism? Again, the first thing is to calculate the base area of the prism, which is a triangle. The formula is a half base times height. The base of the triangle is 10 inches and the height is 8 inches. So a half times base times height will be a half of 10 times 8. 10 times 8 is 80 and a half of 80 is 40, or the area of the triangle is 80 inches squared. Now all we need to do to find the volume is multiply that area by the length it was extended with, which is 50 inches. So we have 40 inches squared times 50 inches and we get 2000 inches cubed. That is the volume of this prism. Next, we find the volume of the cylinder. A cylinder is made by extending a circle. So first, we need to calculate the area of that circle. Area of a circle is calculated by multiplying pi times radius squared. The radius of this circle is 2 meters. So if we square that, we get 4 square meters. Then we multiply it by pi, which is approximately 3.14, and we get 12.56 square meters. Now that we know the area of the circle, to find the volume of the cylinder, we just multiply that area by the length that the circle was extended, which happens to be 10 meters. 10 meters times 12.56 meters squared gives us 125.6 cubic meters. So the volume of this cylinder is 125.6 cubic meters. However, not all three-dimensional shapes are made by extending a two-dimensional shape along the third dimension. Some are made by rotating the shape around its axis, like this sphere. One way to form a sphere is to rotate a two-dimensional circle along one of its diameter lines. Another three-dimensional shape formed by rotating a two-dimensional shape around an axis is a cone. A cone can be formed by rotating a right triangle around one of its two perpendicular edges. To find the volume of a sphere, we use the formula volume is equal to 4 over 3 times pi times radius cubed. To find the volume of a cone, we use the formula volume is equal to a third times height times pi times radius squared. Here is a sphere with a radius of 2 centimeters. That's the only dimension we need in order to find volume. Our formula, volume is equal to 4 over 3 times pi times radius cubed. Cubing the radius means we multiply with itself 3 times. So 2 centimeters times 2 centimeters times 2 centimeters gives us 8 cubic centimeters. Next, we multiply by our approximation of pi, 3.14 times 8, which gives us 25.12 cubic centimeters. Finally, we multiply that by 4/3, which is the same as multiplying by 4 and then dividing by 3, and that gives us a volume of 33.49 cubic centimeters. Now use the formula to find the volume of this cone. And so, to determine the volume of a regular solid, we first measure the dimensions that we need. Then substitute the dimensions in the formula and remember to include the units. In this block, we used centimeters, and so the unit of volume is cubic centimeters. But not all solids are regular in shape, like this rock. Nevertheless, we can still determine its volume. But first, let's look at volumes of liquids. Volumes of liquids are usually measured using graduated cylinders, although beakers, burettes and pipettes are also used. Each of these instruments is graduated with markings. All lines are called the scale. Each line is a division or a graduation, and only some of the divisions are marked. Some of these instruments are more precise than others. The amount of liquid that a given container can hold is called its capacity. Capacity is determined by the volume of the container and is given in liters. To convert volume into liters, we use the following relationships. A container with a volume of 1 cubic centimeter can hold 1 milliliter of a liquid. A container with a volume of 1,000 cubic centimeters can hold 1 liter of a liquid. And a container with a volume of 1 cubic meter can hold 1,000 liters of a liquid. So when you calculate the volume of a container, you can determine how much liquid it can hold. Now let's talk about volumes of irregular solids. To measure the volume of an irregularly shaped object, such as a rock, we measure the volume of the liquid the solid displaces when submerged. So note the initial volume of water in a graduated cylinder. Submerge the irregular object and note the final volume of the water. The difference between the initial volume and the final volume is the volume of the object. In this example, the initial volume was 50 milliliters and the final volume was 81.2 milliliters. The volume of the displaced water is 81.2 minus 50, which gives us 31.2 milliliters. Now, whereas it's widely acceptable to give the volumes of liquids and gases in terms of liters and cubic meters, volumes of solids ought to be given in cubic meters. The solid displaces its own volume of the water, so we convert the 31.2 milliliters into cubic centimeters. If a volume of 1 cubic centimeter can hold 1 milliliter of a liquid, how about 31.2 milliliters? So we have 1 cubic centimeter times 31.2 milliliters over 1 milliliter. The milliliters cancel out and we get 31.2 cubic centimeters. The volume of the water displaced is 31.2 cubic centimeters, and this is also the volume of the rock. Next, we move to mass. Mass is defined as the quantity of matter in an object. The SI unit is kilogram. This is an example of a standard kilogram weight used by different shopkeepers. But the prototype of the standard kilogram is supplied by the International Bureau of Weights and Measure for standardization of masses locally. Different types of balances are used to measure masses of objects of different magnitudes. Other multiples of the kilogram are shown here. Density. Typically, the reason we measure the volume of an irregular solid is to determine its density. Density is mass per unit volume of a substance. Mathematically, density ρ is equal to mass over volume. Using a balance to measure the mass of the rock, we find it's 74.88 grams. We also know its volume is 31.2 cubic centimeters. Then its density is equal to 74.88 grams over 31.2 cubic centimeters, and that gives us 2.4 grams per cubic centimeter. Note that 1 gram per cubic centimeter is equal to 1,000 kilograms per cubic meter. Now, density is a fundamental characteristic of a substance, much like a fingerprint. If you measure an object's density accurately enough, then you can often use that number to help identify what the material is or to determine the purity of a known substance, for example, from such a table. The most accurate way of measuring densities of liquids and most solids is using a gadget called a pycnometer or a density bottle. It consists of two pieces, a small flask and a glass stopper with a built-in capillary tube. When you fill the flask to the neck bottom and then insert the stopper, the liquid is forced up to the tip of the capillary. Dry off any spillage and the liquid is guaranteed to occupy a volume that is very precisely prescribed. Once you determine what that volume is, it is simple to measure the density of the liquid by simply measuring its mass. And you can do the same with most solids as well. So let's do a demo. First, we measure the mass of the bottle when it's clean, dry and empty. This is 16.7 grams. We then pour distilled water into the flask slowly to fill it completely without bubbles sticking to the sides. Stop when the liquid comes just up into the neck. When you put the stopper, some of the liquid will be pushed up into the capillary tube. Dry off the spillage and the bottle will be precisely filled with water. Next, we measure the mass of the filled bottle. Subtract this mass from that of the empty bottle to get the mass of the water. It's 25.0 grams. Now we calculate the density of water. 25 milliliters is equivalent to 25 cubic centimeters. So the density of water is 25.0 grams over 25 cubic centimeters, giving us 1 gram per cubic centimeter. Now let's use this method to find the density of a solid that doesn't dissolve in water, like these steel beads. Pour the beads into the bottle and take the mass of the bottle plus the beads. That is 121.0 grams. Subtracting the mass of the bottle, 121.0 minus 16.7 grams gives us 104.3 grams. Next, we fill the bottle with water and measure the mass again. It's 138.3 grams. That means the additional water is equal to 138.3 minus 121.0, giving us 17.3 grams. Now, since we know both the mass and the density of the water added, we can calculate its volume. Density is equal to mass over volume, so volume is equal to mass over density. That will be 17.3 grams over 1 gram per cubic centimeter. That gives us 17 cubic centimeters. Again, We know that the total volume of the bottle is 25 milliliters or 25 cubic centimeters. If the water takes 17 cubic centimeters, then the beads must have taken 25.0 minus 17 cubic centimeters, which is equal to 8 cubic centimeters. So the density of the beads is equal to mass of the beads over volume of the beads, 104.3 grams over 8 cubic centimeters. That gives us 13.0375 grams per cubic centimeter. Next, densities of mixtures. Now, when you put two or more substances together that do not react with each other, you get a mixture. For example, sand, cement, and ballast. Because each constituent of a mixture has a different density, then the mixture will have a new density. Here are facts about mixtures. The total mass of the mixture is equal to the mass of A plus the mass of B. The total volume of the mixture is equal to volume of A plus the volume of B. And thirdly, the density of the mixture is equal to the density of A plus the density of B, right? Wrong. Now, whereas the volume and mass of a mixture is the sum of its constituents, the density is not. It is calculated from the new masses and volumes. Let's take an example. 1,800 cubic centimeters of fresh water of density 1 gram per cubic centimeter is mixed with 2,200 cubic centimeters of seawater of density 1.025 grams per cubic centimeter. Calculate the density of the mixture. Now, density is equal to mass over volume. So we need the total volume and mass. Total volume is straightforward. 1800 plus 2200 gives us 4000 cubic centimeters. To get the masses, we need to calculate. Since density is equal to mass over volume, mass is equal to density times volume. So mass of the fresh water is equal to 1 gram per cubic centimeter times 1,800 cubic centimeters. That gives us 1,800 grams. Mass of the seawater is equal to 1.025 grams per cubic centimeter times 2,200 cubic centimeters. That gives us 2,255 grams. The total mass will be equal to 4,055 grams. Overall density is equal to 4,055 grams over 4,000 cubic centimeters. That gives us 1.01375 grams per cubic centimeter. And finally, time. In laboratories, time intervals are measured using either a stopwatch or a stop clock. A digital stopwatch is preferred due to its accuracy. A good experiment that requires measurement of time intervals is, for instance, the time taken for a pendulum to make a given number of cycles.